So now I'm going to go into DualEELS. So if we want to do DualEELS, it's very straightforward. In the eels palette, you can see at the top we have next to the button that's highlighted blue at the moment, it's called single, we have DualEELS. So if I select dual, the palette looks pretty similar, but you can see main difference is that we now have two acquisition parameter sets, so one for low, one for high. So we can set 2 energy offsets and 2 exposure times. So I'm going to go ahead and start the view. At the moment, we're looking at 2 low loss spectra, which isn't particularly useful. So I'm going to apply an energy offset to the high loss. And then what's really useful here, so if I change my frame exposure back, so this would be the intensity that we'd have in this core loss region. So if we look at the right-hand spectrum, if we were to have the same frame time as we have for the low loss, so imagine we were doing single eels, this is what our core loss would look like. But what's really great here is that we can change this time, because now we're no longer now having our zero loss peak in the field of view. So if I go to something like 10 milliseconds, now we start to have usable kind of signal in the core loss region. So we can already see our boron K edge and our nitrogen K edge in the spectrum. Okay, so DualEELS helps us in terms of dynamic range, also helps us in terms of energy range. So our energy range is extended now because we have 2 spectra instead of 1. The maximum offset that we can apply here is 2000 EV. For this particular sample, this isn't very useful because we don't have any signals out at this super high energy loss that we're very interested in. So I'll go back to 250 EV. Final reason why it's really great to have DualEELS is because we can have our low loss spectrum as well as the high loss spectrum. Remember that that's really important. It allows us to do things like thickness compensation, deconvolutions, and that's what I'm going to go into next. One other thing that's really useful when we have the low loss spectrum is we can use the ZLP lock function that we've already seen. So if I switch on ZLP lock, then that zero loss peak, I'm moving the chair around, you can see, stays at channel 200. So 0 is fixed at 0 and it's a live on the fly correction. In DualEELS, that's really great because that correction is, as well as being applied to the low loss spectrum, it's actually applied to the high loss spectrum. So we can be confident that the data that we're looking at is at the correct energy scale or energy offset. Okay, so I'm going to leave ZLP lock switched on. And then let's just kind of have a little recap. So let's verify that the thickness is okay in this region, so we can use EELS analysis palette again. So I'm going to select the low loss spectrum, switch on thickness. Yep, the thickness is still good. The sample hasn't drifted or anything, so nice and thin. We're good to continue. So you can see some other buttons to the far right-hand side of the EELS analysis palette. One that's actually pretty fun to use is the splice. So I'm going to increase the exposure time a little bit for the high loss. And then now if I press splice on the DualEELS pair, or either of the components, it does a live splice of those two. So now we're looking at a kind of a live spectrum that's spliced together. So it's the 2 spectra spliced together. And it gives us kind of our extended energy range, and everything's kind of in the same spectrum there, which can be useful for certain processing. So let's switch off the splice, and I'm going to close the spliced image. You can also see that there's a deconvolve option. So if I select the low loss and then enable deconvolve, what happens is we're doing a live log deconvolution, so a Fourier log deconvolution on the low loss spectrum. So we can see in pink we have the deconvolved spectrum, which is the single scattering distribution. So we can see that this kind of the difference here between the pink and the teal is the pleural scattering. I'll go and switch that off, and then let's move on to the high loss. So we can do the same thing here. If I draw a background window, because remember we have to have an extracted signal for the ratio deconvolution, then deconvolve, and again we have a live deconvolved spectrum. So we have the single scattering distribution in pink, kind of our raw in teal, and kind of our uncorrected or kind of undeconvolved is in green. So this is a live Fourier ratio deconvolution. And again, that's something neat that we can do with the EELS analysis palette. So I'll go ahead and switch off the deconvolution. Now I'm going to get rid of my background window. Let's go back down to the faster frame time of 10 milliseconds for the high loss, and I'll leave it at 0.2 milliseconds for the low loss. Now I want to do a capture. 5 seconds is the current capture time. I'm happy with that, so I'll just hit capture. And let that acquisition run. Go to the analytical workspace, and there we have our data. So we could use the splice here if we wanted on the capture data. I'm not going to do that. I want to do a quantification. So we can do quantification on single EELS, we can do quantification on dual EELS. Let's see what the difference is when we do it with dual EELS. So I'm going to select the high loss spectrum and open the elemental quantification palette. Then I'm going to populate the edge list a little bit differently this time. So I'm going to use the periodic table button here. Select boron and nitrogen. Then close that. Now let's go to the edge setup. So again, I need to tweak the window for the nitrogen. And looks like we have some sort of divergence from the fit here. One thing that you see that is different, and let's just check the boron first, is that we have this option now, include pleural scattering. So as we saw in the lectures, when we have a dual EELS pair, we're able to correct for pleural scattering. So rather than do a deconvolution and remove the pleural scattering, what we're doing is a forward convolution of the low loss with the Hartree-Slater cross-section model to kind of make that edge shape a little bit more true to reality. So you can see if I switch off pleural scattering correction, this green is kind of a basic K-edge shape. Switch that back on, and then you can see how that shape is modified by this pleural scattering correction. So generally, it's good to try and account for the pleural scattering. So that's a nice feature. Okay, so I'm going to go ahead and hit quant. Then, okay, so now the quant results are in the quant, or in the results window. So let's just have a little walk through that. We've got approximately similar percentages to before. Maybe it's a little bit different because my windows are not exactly the same as I had before. But as well as the relative composition that we have here, so these atomic concentrations, if we look to the right, we now have areal density, which is in atoms per nanometer squared, and volumetric density, which is atoms per nanometer cubed. So the reason that we have these extra quantification results is because we have the low loss, so we're able to do absolute quantification and not just relative quantification, as is the case for single EELS.